Welcome everyone to this presentation. My name is Massimiliano Taverna, and together with Professor Kenneth Paterson from ETH Zurich, we have found some practical attacks against the most widely used implementation of the Ethereum protocol. And today I'm happy to be here to discuss them with you. So what's Ethereum? Well, Ethereum is the most popular blockchain nowadays for decentralized application, as we also saw in the previous two talks. And if you want to run your own node so that you can directly interact with the Ethereum blockchain, then chances are you will use a software called Go Ethereum, which is an official implementation of the Ethereum protocol written in the Go programming language. As a statistics, 80% of all Ethereum nodes before the merge were using Go Ethereum. The merge was an event in the history of Ethereum where the system switched from proof-of-work mechanism to a proof-of-stake mechanism, which ensures chain immutability. But even after the merge, there are still nowadays blockchains, for example, Ethereum Classic, which uses the original proof-of-work implementation of Ethereum. And in these contexts, the dominance of this software is even higher. And all of this is important for our research because our attacks specifically target Go Ethereum and they specifically target the proof-of-work implementation. So before jumping directly to the attacks, let me just give you a few explanations about a few concepts related to Ethereum security, starting by the peer-to-peer network of Ethereum. So as we are talking about blockchains, we're talking about distributed systems. We have a network of nodes that talk to each other. All these nodes need to have a copy of the blockchain, hopefully the same copy of the blockchain, otherwise something is not working correctly. And the blockchain defines the Ethereum, the so-called Ethereum state. So a huge data structure which contains all the account balances as well as all the smart contracts, their code, and their data. And an Ethereum client is the software that the node needs to run if you want to manage the blockchain and the Ethereum state. So Go Ethereum is an Ethereum client and is the most widely used. Another very important concept about Ethereum security is so-called proof of work. So whenever you want to create a block, you need to find a number which you append to this block, and then you compute a hash over this block, and if this hash satisfies some constraint, then it means that the proof of work is valid. Otherwise, you need to try again with a different number. And the hash function we're talking about here is called ETHash, which is an Ethereum-specific hash function. It's a slow hash function, but still, because of its characteristics, there is no better strategy than just trying random numbers until you hit on a valid proof of work. And when you do so, you say that the block is valid and you can go on and mine the next one. So in the end, as satisfying this constraint is quite hard, you need to take multiple attempts, and in the end, this proof of work is evidence that you have put some computational effort into the creation of the block. And then you can combine this concept with this rule, which very simply says that among all the chains that are available in the network, you should use and operate on the longest one. And this basically makes the system secure as long as we work with the assumption you can see in the slide. So as long as the majority of the computational power is in the hands of the honest nodes, then it means that the longest chain is also the honest one. And every Ethereum client needs to be implemented such that the longest chain is used. Another very important mechanism that every Ethereum client needs to implement is so-called chain synchronization. This means that whenever a new node joins the Ethereum network, it doesn't have a copy of the blockchain yet, and it doesn't have a copy of the state of Ethereum yet either. So it needs to download and verify all the blocks from its peers. But this process has a bottleneck, namely that verifying blocks means verifying proof of work, and verifying proofs of work means to run that slow hash function I was talking about before. So this makes the entire process quite slow. And Go Ethereum developers have found a solution, which is a probabilistic verification algorithm where not all the proofs of work are verified, but just some blocks are chosen at random and uniformly at random. And for these blocks, the proof of work is verified, but not for the other ones. And on average, we are talking about one block in every 64 which undergoes this proof of work verification. So that said, we can jump to the attacks. Our attacks target synchronizing nodes, so nodes that are undergoing this process of downloading and verifying blocks, and not nodes that are already in sync with the network. And the goal of our 3 attacks is always the same, namely to take a victim node onto a malicious fork. And as I told you before, the chain is what defines the Ethereum state. So if a victim is on a chain or a fork controlled by the adversary, then it means that the adversary also has control over the state that the victim sees. And this means that the attacker can completely alter all the account balances and all the smart contracts code and data to the eyes of the specific victim chosen. So as an example, imagine that the attacker Eve has only $10 on the real chain, the honest chain that everyone is using, but the victim Alice is after one of our attacks on this malicious fork, and so she believes that Eve has, let's say, $1 million. At this point, imagine also that Alice is selling something like a car and she is willing to accept payments via Ethereum. Then, of course, the attacker Eve can forge a transaction and send some money to Alice, and Alice will see her account balance increased and now will be glad to give her car to the attacker. But actually the attacker has given no real money to the victim because on the real honest chain that everyone else is using, her account is just $10 and has stayed $10 for all this time. So the first attack we have has the assumptions you can see in the slide. The first one is the most important one. So we require an attacker with some computational power, namely 1.6% of the entire computational power of Ethereum, which on one hand is a lot, it amounts to many, many GPUs, but on the other hand, it's not a lot, meaning that there were miners in Ethereum which had even more than these computational power, and there are miners in Ethereum Classic which have it. And then we also need at least 2 malicious nodes to be in the set of peers of the victim. And then the last assumption is what I was talking about before. So the victim still needs to undergo this synchronization process. The vulnerability lies in the probabilistic verification algorithm I was talking about before. And if you were to look at it, you would notice that the very first thing that Go Ethereum does is to use a cryptographically secure pseudorandom number generator to pick some random integer. And so far, so good. It looks like a good start. However, then they use this number to seed an insecure PRNG or a weak PRNG. And as we know, this doesn't make the weak PRNG secure. Furthermore, the Go implementation of this weak PRNG internally reduces the seed to just 31 bits. So whatever seed you pass, you just use 31 bits of this number, which makes the seed space very small. And it basically allows for exhaustive search in this space. And then Go Ethereum just goes on by using this seeded instance to choose which blocks will undergo proof of work verification. And if we combine this with the fact that a node, while synchronizing, leaks information about the outputs of the PRNG, and you can find more details about this in the paper as well, then what an attacker can do is to collect this information and search in the seed space, the seed which can produce the same information he's observing coming from the victim, and uniquely identify one seed. And after recovering the seed chosen by the victim, he can then predict all the choices, all the random choices that the victim will do. This allows for mounting an attack where the victim starts the synchronization, downloading the blocks. The attacker A starts to create new blocks. And since A knows which blocks will be verified, then it will just compute a proof of work for those blocks and not all the other ones. And as on average just one block in every 64 is verified, it means that if the attacker can mine one block faster than what the other miners need to mine 64 blocks, in the end, the attacker can create a longer chain than the honest one. Of course, this chain is invalid, but to the eyes of the victim, it will be valid. And according to the longest chain rule, then the victim will choose to operate on this chain instead of the honest one. And you see also why we need at least 1.6% of the total mining power, because it's an approximation of 1/64. The second attack we have has some more relaxed assumptions. You can see that the fraction of the total mining power is a bit lower. We just need one malicious peer in the victim's peer set, and we still need a victim that needs to undergo synchronization. This attack exploits some very specific details of some mechanisms in Go Ethereum, so I will not go into the details now, but I would invite you to read them in the paper. And what's interesting here is that this attack is enabled by the countermeasure to another attack. So Go Ethereum developers in the past found an attack and they tried to patch it, but while they were patching their code in one place, they actually opened another vulnerability in another place. And then the third attack came from the idea of combining the two flaws we observed and we used respectively for the first two attacks. And surprisingly, what we got is a very, very low computational power needed by the adversary, where just with 5 GPUs, you could achieve the same goal as the previous two attacks against Ethereum, and just with 1 GPU, you can do the same on Ethereum Classic. If you want the exact number, is on the order of, the fraction is on the order of 10 to the -7, so really, really smaller than the one required by the previous two attacks. We disclose, of course, our vulnerabilities to Ethereum, Ethereum Classic, and Ethereum Proof of Work. Ethereum was not so interested in them because they had already switched to Proof of Stake, but Ethereum Classic was very collaborative with us. While, unfortunately, Ethereum Proof of Work did not respond to our attempts to contact them, so their software is still vulnerable today. And the conclusion we drew from our analysis is that Web3 is still a new dynamic environment, and things actually mistakes are bound to happen again and again if we don't take more security more into account, because the vulnerability we observed are not very new. So, for example, the first one is the usage of a weak PRNG. The second one is closing a vulnerability and opening a new one. So these are mistakes that could be avoided, that can be avoided in more classical software engineering environments. These are avoided. But since of the fast-paced environment that Web3 is, we really need to take security more into account. And with this, I am at the end of the presentation. So thanks for listening. And now I'm open to your questions.
Thank you.